Great. Thanks, Tony, for the introduction. Welcome to this session of the physical oceanography team, and it's jointly with the modelers and the systems team. So IARPIC, for those of you who are not familiar with IARPIC, is the Interagency Arctic Research Policy Committee that brings together leaders from many agencies, departments, and offices across the US federal government to enhance collaboration on research in the Arctic. So IARPIC Collaboration is the public branch of IARPIC, and that aims to facilitate interagency communication, coordination, and collaboration to advance Arctic science. So the physical oceanography community of practice aims to facilitate the exchange of information and encourage new collaborations on the physical oceanography of the Arctic Ocean across agencies. And we do that primarily through the organization of monthly webinars like this one. So as I said, this is a joint meeting between the physical oceanography and the modelers community of practice and the systems collaboration team. So in today's session, we'll discuss the interactions between the Atlantic Meridional overturning circulation and the Arctic Earth system. And this recognizes the fact that the Arctic does not operate alone, but is strongly connected to the lower latitudes through the atmosphere and the ocean in particular. Exchanges of heat and fresh water between the lower latitude oceans and the Arctic are strongly coupled and have the impact of global implications. So today we'll have two very distinguished speakers to talk about this subject. The first speaker is going to be Yuxi Li. She is a graduate student at the University of California, Riverside, working in a group of Wei Lu. She is going to be talking about our recent paper on the impacts of Atlantic Meridional overturning circulation weakening on Arctic amplification. So with that, I'd like to hand it over to Yuxi.
Okay, thank you. Thank you, Wilbert, for the introduction. So let me share my screen here. Okay. Okay, so hello everyone. I'm Yuxi Li from University of California, Riverside, as Wilbur introduced. So today I'll be sharing our recent work on how a weakening Atlantic Meridional overturning circulation, what we call the AMOC, influences on the Arctic amplification. So this research is a collaborative effort with my advisor, Professor Walu, and the co-authors Alex Fedorov, Nicole Fedor, and Patrick Tyler. So Arctic amplification refers to the phenomena whereby Arctic surface air temperatures increase at an enhanced rate relative to the rest of the globe. Minop and Weatherall first identified this in 1975 using early climate model experiments, and since then, multiple lines of evidence have confirmed it as one of the most robust features of the climate system's response to external forcings, such as rising greenhouse gas concentrations. So the panel on the right illustrates the Arctic warming trend from 1979 through 2014 across observations, reanalysis product, and the climate model simulations, underscoring the consistence of this amplified warming in the Arctic region. Although Arctic amplification has been recognized for decades, this pronounced warming of the Arctic is a much more recent phenomenon. So on the left, you can see surface air temperature anomalies for both the Arctic and the global mean. So we can note that how the Arctic has warmed much more sharply than the global averages since the early 1980s. And on the right, the figure reveals the Arctic shifting from a cooling trend to a warming trend in less than a decade, which also indicates a dramatic climatic shift in the 1970s. So the Atlantic Meridional overturning circulation, or the AMOC, function like a giant conveyor belt in the Atlantic. So its upper limb carries warm, salty surface waters northward via the Gulf Stream at the North Atlantic current, transporting vast amounts of heat into higher latitudes. And there that the water cools, becomes denser, sinks, and forms the deep return branch that flows southward. And this overturn circulation plays a key role in modulating northern hemisphere climate. Recent observation records, such as those from the rapid rate at 26° north and various paleo proxy reconstructions, show that the AMOC has weakened over the past few decades. With observations and proxy records pointing to a recent slowdown of the AMOC, that our study asks, how does that weakening feedback on Arctic amplification? So to isolate the AMOC's role, we use paired ensembles of fully coupled CCSM4 simulations with a free AMOC set that evolves without intervention, and a fixed AMOC set in which we apply a freshwater flux adjustment to hold the overturning strength constant. And each ensemble comprises 5 members to capture internal variability. And the free AMOC runs comes from the CMA5 archive, and our fixed AMOC experiment branch off from those simulations in 1980. From that point onward, that's indicated by the green shading on the map here, that we gradually remove fresh water in the North Atlantic to counteract the weakening, thereby stabilizing the AMOC strength. And by computing the difference between the free and the fixed AMOC ensemble means that we directly quantify how a weakening AMOC impacts on the Arctic amplification. So the figure here shows the temporal evolution of AMOC strength on the top and surface air temperature anomalies in the Arctic on the bottom. So the blue line here represents the weakened AMOC, showing a decrease in the AMOC strength over time, while the red line here represents the stable AMOC simulations. And from the surface air temperature, we could see a gap in warming between the two simulations, widens after 2030s and peaks by the end of the century, indicating that a weakened AMOC can temper Arctic warming. And hence, for this study, we will mainly focus on the last 2 decades of the 21st century, which will be between the 2081 to 2100. And the figure on the top here shows the spatial pattern of surface air temperature changes between 2081 and 2100, which the right panel shows. The right panel here shows the difference between 2 simulations, which indicates that the AMOC, the Arctic tends to stay cooler when the AMOC is weakened. And the figure on the bottom shows the zonal average annual mean surface air temperature changes here and the amplification factor, which is the ratio of Arctic to tropical temperature changes. So between 2081 and 2100, a weakened AMOC is projected to reduce Arctic warming by 1.37 degrees Celsius, which corresponds to a 0.36 degrees in the amplification factor. And seasonally, this cooling effect is most prominent during the cold seasons from December to March. And by using the radiative kernels, that we could identify the main feedback processes. So the upper panels show the annual mean partial temperature contributions from both simulations, where the vertical axis shows the Arctic and the horizontal axis shows the tropics. So for both free and fixed AMOC simulations, the effect of each feedback mechanisms are similar, and the only difference is in their magnitude, where we can see the surface orbital feedback in the green dots here is the main driver of Arctic warming for both simulations. and followed by the Planck and the lap-spread feedback, while the shoal wave feedback and ocean heat uptake act as cooling agents. Now, the lower panels show the differences between the two simulations. So from left to right are showing in the annual mean, boreal summer, and boreal winter. From these panels that we identify three major contributors to the reduction in Arctic warming: the surface orbital feedback, ocean heat uptake, and temperature feedback. So the AMOC-induced cooling through the orbital feedback is most prominent during the boreal summer, as we can see here. The green dot during the summer has the largest value, whereas the ocean heat uptake is most prominent in the boreal winter. And on the other hand, that we could see the atmospheric energy transport and the shoal wave cloud feedback will slightly offset this reduction in the Arctic warming. So the figure here shows the spatial pattern of the annual mean partial temperature contribution for each radiative feedback. And we first focus on the surface orbital feedback. The figure on the center here shows the differences of sea ice concentration changes from top to bottom are showing in the annual mean boreal summer and boreal winter. And the figure here at the right shows the corresponding seasons changes in surface orbital feedback. So we could find that although the AMOC-induced reduction in sea ice loss is most pronounced in boreal winter, but with limited solar radiation, that the AMOC-induced cooling through surface orbital feedback is most prominent in the boreal summer. And we also analyzed the ocean temperature budget, which is shown in the upper panels. And from left to right are the whole depth integrated ocean temperature tendencies induced by advection and diffusion, surface heat fluxes, and the net tendency. So the panels at the bottom are radiation fluxes at top of atmosphere, surface, and the atmospheric energy convergence and divergence. From the upper panels, that we could find that the AMOC weakening will lead to ocean heat transport divergence and the whole depth water cooling. We're showing in the negative values in this panel here. And we could see atmospheric energy convergence. The positive value here is trying to compensate the cooling from the ocean heat transport divergence through the ocean heat uptake. So we could see the positive value here means that more heat is absorbed from the ocean. However, the cooling induced by the ocean heat transport divergence outweigh the compensation from the atmosphere and result in a net cooling tendency in the ocean temperature, which further leads to a lessened sea ice loss. Now we focus on the temperature feedbacks. So from Planck feedback that we could see a general cooling in the central Arctic and its neighboring regions, but a warming in the North Atlantic warming hole region. And this geographic distinction reveals that the Planck response is weaker over the North Atlantic warming hole in the free AMOC simulation, leading to a more significant anomalous warming effect than in other regions due to the strikingly colder surface temperature in this area. As for the lap-spread feedback, it shows general cooling in both the Central Arctic and the North Atlantic warming hole region. This AMOC-induced cooling through lap-spread feedback is because of the stronger cooling of the surface and lower to mid troposphere and the relatively weaker cooling in the upper troposphere. So in the North Atlantic warming hole region, that the warming from Planck feedback is largely offset by the cooling through lap-spread feedback. And the AMOC-induced cooling is partially offset through the shoal wave cloud feedback, that we could see a general warming from the shoal wave cloud feedback in the Central Arctic and a cooling in the North Atlantic warming hole region. So the figure on the right shows the changes in cloud friction of low-level clouds and mid to high-level clouds. We could find the warming in the Central Arctic is because of the reduction in the low-level clouds and hence decrease in the reflection of the solar radiation. On the other hand, that in the North Atlantic region will be an increased, the cooling effect in the North Atlantic warming whole region are caused by the increased low-level cloud friction and hence the increase in the reflection of the solar radiation. So in summary, that AMOC weakening leads to a slower increase in Arctic surface temperature, reducing projected warming by 1.37 degrees Celsius by the end of the 21st century. And the main drivers of reduced warming are surface orbital feedback and ocean heat uptake changes, particularly during this boreal summer and the winter respectively. With the ocean temperature and heat budget analysis that we found, the AMOC weakening leads to ocean heat transport divergence and whole depth water cooling. This results in less heat being carried northward and an increase in ocean heat uptake, which leads to surface temperature cooling and reduced sea ice loss. Additionally, that the AMOC slowdown has led to strong surface and lower to mid-troposphere cooling through left-right feedback and slightly warming in the Central Arctic through the shortwave cloud feedback. So I will start here. Thank you for your attention.
Great, thank you so much, Yushi. It was a very interesting presentation. A lot of things to digest. Let's open the floor for maybe 4 minutes of Q&A before we hand it over to our next speaker. Please raise your hand if you have a question for Yushi. Twila, I think you have your hand.
Yeah, hi. Thanks so much. That was interesting and admittedly a lot of information to take in to someone who doesn't specialize quite in this field. But I am curious about the extent to which the kind of model results that were most commonly seen coming out of Earth system models already incorporate this information, and now you're having a new understanding of the mechanisms and the processes and connections within that information, or whether you feel like some of these processes and mechanisms aren't being seen in kind of, most commonly produced Earth system model results. And so there's a change in kind of our projection knowledge that comes out of it, which I'm not quite clear on kind of which end we should be kind of extending our knowledge here.
Sorry.
I don't mind. I have kitties too.
Okay. Yeah, so I think your question is asking that whether our mechanisms behind this is different from the other general climate models outcomes. Am I understanding that correctly?
Yeah, just in kind of the way that you were going about sort of your, free or mixed and thinking about those, what's going to be a usual practice in most Earth system model results? And are they going to essentially provide the output and the results that you're providing? And we have this new understanding of the processes and interactions and how we're getting to those different future Arctic warming temperatures, those sorts of things? Or is there something here too that needs some tweaking in regards to our understanding of what were kind of most commonly projections that we'd see?
Okay, I think I'm not sharing the screen right now. Let me, sorry. She wants to participate. Okay. Okay. So I think from the showing here that our free AMOC simulation, which has the weakened AMOC situation here, that is coming from the CME5 collections, which will be the normal general climate models outcomes. So in that case, that is under the the RCP 8.5 external forcing. So under the warming climate, that the AMOC will be weakened. So it's showing the time series here that the free AMOC will have a weakened AMOC in the future. And in our simulations, that those experiments are branched from this weakened AMOC, but we gradually remove the fresh water in the deep water formation area to maintain its strength. So back to your question, I think the key feedback mechanisms are pretty similar in both simulations. The only difference is their magnitudes. So for example, here with AMOC, with maintaining AMOC strength in its 1980s value, that the orbital feedback will be much stronger than with a weakened AMOC. So yeah, I hope this answers your question.
Yeah, thank you.
All right, but thank you very much. How about we move on to our next speaker and then leave additional questions either to the discussion afterwards or feel free to put them in the chat. So our second speaker is Camille Hankel at the University of Washington. She has a PhD from Harvard University last year. And she's currently a postdoctoral fellow at the University of Washington. The title of her talk is Arctic sea ice meltwater as forcing and feedback on the Atlantic meridional overturning circulation. Right.
Thanks so much, Wilbert. I will now share my screen. All right. Thank you everyone for being here, and thanks to the organizers for giving me the chance to talk about my work. So as Wilbert mentioned, my name is Camille and I'm a postdoc at the University of Washington. And most of what I'll be showing today is work I've done in collaboration with my two postdoc advisors, Cecilia Bitz and Wei Cheng. And this work is funded by the Cooperative Institute for Climate, Oceans, and Ecosystem Studies at UW and through the NSF Atmosphere and Geospace Sciences program. So let's see if I can advance here. There we go. Yuchi set things up really well for me, so I'll go very briefly through the introduction here. But as you all know, the Atlantic Meridional Overturning Circulation, or AMOC, is this really important ocean circulation in the Atlantic. But it affects, as Wilbur introduced, not only the Atlantic region and the North Atlantic climate, but also the Arctic climate and ecosystems through its modulation of nutrient and freshwater transport and heat into the Arctic. And it's projected to slow down under future warming scenarios. The title of today's webinar was something along the lines of two-way AMOC Arctic Earth System interactions. So I kind of want to situate this talk in the context of those interactions. So Yuchi started us off with a lot of focus on this arrow here. In other words, how the AMOC can affect the Arctic, Arctic amplification, and Arctic sea ice. In particular, through the mechanism where a slowdown of the AMOC, which we project for the future, can lead to a reduction of ocean heat transport into the Arctic, which leads to cooling that's further enhanced by atmospheric feedbacks. And she also has this other great paper attributing some of the observed sea ice loss to this phenomenon. And so for this talk, I'll be focusing a little bit more on this arrow here, which is how the Arctic, and in particular Arctic sea ice meltwater, can in turn influence the AMOC, and then how these two things work together in a positive feedback cycle. So I want to review a little bit the AMOC and its possible changes due to the importance of surface buoyancy forcing on the ocean. So the AMOC is in part driven by negative buoyancy fluxes over the North Atlantic that help form dense waters and drive deep convection. So in particular, these warm surface waters travel north to the North Atlantic, where they undergo significant cooling to the atmosphere, which in turn makes those surface waters denser and heavier, which drives this deep convection motion. And then that connects to the return flow of the overturning circulation. And under increases in CO2, we expect this process to be somewhat disrupted, both due to less cooling at the surface and due to enhanced freshening due to changes in the net precipitation over the North Atlantic region, which can potentially reduce this sinking motion. Now, Arctic sea ice stands to potentially influence all of these processes. Both the mean state and the retreat of Arctic sea ice under increases in CO2 can influence those freshwater fluxes into the ocean directly, by which I mean through the meltwater of sea ice itself, and indirectly by modulating how much of the ocean is exposed to these precipitation changes. It can also influence the ocean's exposure to surface heat fluxes and to wind stress, which in turn influences the vertical mixing of heat. Now, in this talk, I'm going to be focusing specifically on just one of these processes, which is how the sea ice meltwater can interact with the AMOC. So I want to introduce a concept that has sometimes been referred to as an Arctic freshwater conveyor belt. And the idea here is that in the high Arctic, there is a balance of sea ice freeze up and export. In other words, you have ice thermodynamically being formed due to the cold temperatures in the high Arctic, and then being mechanically exported out of the Arctic and into the North Atlantic. And in the North Atlantic region, there's a balance of sea ice import and melting. In other words, although there's not significant amounts of thermodynamic freeze up of sea ice there, there's still a lot of sea ice that is being introduced through this mechanical import of ice from the higher Arctic. And what this means is that this forms a mechanism by which fresh water can be transported from the Arctic out into the North Atlantic, where it can potentially influence those deep convection sites. And I want to highlight that this is a little different than a lot of work that I see on liquid freshwater pathways. In other words, how freshwater, either from ice, land runoff, rivers, in liquid form percolates and makes its way to different parts of the Arctic or North Atlantic. Here I'm talking about the export of ice in solid form that then goes out to the North Atlantic and melts there. And one potential implication of this is that if you have an increase in Arctic sea ice and an increase in ice production in the high Arctic, this can lead to increased ice export, which is more ice reaching the North Atlantic and melting there. And conversely, if you have a decrease in sea ice, this can lead to less ice reaching the North Atlantic and less freshwater input there. So I want to really dive into this mechanism of this ice export and its influence on the AMOC. And in particular, I'm aiming to explore and separate the effect of this local sea ice meltwater as a forcing and a feedback, as my talk title introduced, on the AMOC under increased CO2. And then I'm hoping to apply this knowledge to help explain the AMOC's response to different rates of CO2 change, which is something I'll explain. So first, just a few definitions. By local, again, I mean this sea ice that leaves the Arctic in solid form and then melts locally, as in local to the deep convection sites in the North Atlantic. And by forcing, I mean these meltwater changes that occur because sea ice is retreating due to CO2, then there are meltwater changes that may potentially influence the AMOC. By feedback, on the other hand, I'm referring to when sea ice changes occur because of the AMOC changes, and then those sea ice changes influence the AMOC via this meltwater. So I'll introduce here my experimental design. So I'm focusing on the transient and long-term behavior of the AMOC under different rates of CO2 change. And this is an idea that I'm kind of been interested in more broadly beyond this project. But for the AMOC is motivated by some recent work that shows the AMOC has very different sort of multi-centennial versus quasi-equilibrium millennial scale responses to an instantaneous change in CO2. So we might think that there are some interesting behaviors that happen when instead you probe the system with different rates of CO2 change. In addition, I think the rate of CO2 change, sort of separately from the magnitude of CO2 change, is a relatively uncertain future forcing scenarios that's worth exploring. So I'm going to look at this in the community Earth system model, very similar to the model Yushi was using, in a coarse resolution configuration due to the computational limitations. And I'm conducting 7 different experiments where CO2 is increased to a doubling relative to pre-industrial at different rates. So the magenta lines here show the atmospheric CO2 being increased more slowly over nearly 1,000 years versus the blue lines show it being increased more quickly. And after that, in all experiments, the CO2 is held fixed until the climate, in particular the AMOC, reaches a quasi-equilibrium. So here I'm showing the strength of the AMOC in those, in total 8 different experiments. And the dashed lines show the year in which each experiment reaches a doubling of CO2, after which the concentrations are held fixed. So what we see is that the level of AMOC weakening depends on the rate of CO2 increase, even though we're increasing the CO2 by the same amount, which is 1 doubling. And in particular, the more gradual CO2 ramping experiments lead to less AMOC weakening, and the more rapid CO2 ramping experiments lead to a stronger AMOC weakening. So this is work that I did in this paper that came out earlier this year, where I really dove into the physical mechanisms that explain what I'm calling this rate sensitivity. So I'm going to skip over the details and just sort of give you the answer of what I found there, because it turned out that it all came back to Arctic sea ice again. So in this work, I proposed an AMOC sea ice positive feedback cycle that enhanced AMOC weakening under rapid CO2 rates. And this is how that feedback cycle goes. So there's initial surface warming from the increase in CO2 that leads to AMOC weakening via a reduction of those North Atlantic upper ocean densities and disrupting that deep convection process. The AMOC weakening under rapid CO2 changes then leads to significant reduction in ocean heat transport, similar to Yuchi's work, which is enough to induce high latitude cooling that actually transiently grows the Arctic sea ice, despite the fact that you're in a warmer climate. And this transient growth of the Arctic sea ice, it can be thought of as an acceleration of this freshwater conveyor belt process that I introduced, that leads to an increase in ice export to the North Atlantic, where that ice melts and induces additional freshwater, which further freshwater in the North Atlantic, which further weakens the AMOC. So this forms a positive feedback cycle between AMOC and sea ice meltwater. Now, interestingly, I found no evidence of this feedback in the more gradual CO2 ramping experiments, in particular because for the same amount of AMOC weakening, there was not as much of a reduction in ocean heat transport. And what this means is that there was never any significant high latitude cooling or sea ice regrowth, which meant there was no extra sea ice meltwater, no acceleration of this conveyor belt to further weaken the AMOC. So with that in mind, I'm moving to the more current work, where I'm trying to use some targeted mechanism denial experiments to better understand the role of sea ice meltwater in this positive feedback. So the goal now is to quantify the role of sea ice meltwater as a forcing and feedback using these mechanism denial experiments, where I suppress the feedback in this model and see how the AMOC responds to rates of CO2 change. So I'm going to break the feedback cycle by prescribing sea ice meltwater fluxes as opposed to allowing them to evolve in a coupled fashion. And from now on, this is work that we've submitted recently to the Journal of Climate. So the way I'm running these experiments is to set the sea ice meltwater in this North Atlantic box, highlighted in red, to a prescribed seasonal cycle. So in other words, we're partially decoupling the ocean from the ice. And by doing so, while the sea ice can evolve according to the CO2 changes and the AMOC changes, the sea ice meltwater felt by the ocean does not evolve in response to that. And here's how we're going to do that. So here I'm showing the sea ice meltwater flux over that North Atlantic box. Now I'm just focusing on the most gradual and most rapid CO2 ramping cases. So I'm taking the two end members. And the black lines show the sea ice meltwater in the original coupled experiments. And we see that when CO2 is increased gradually, you just have this overall linear decline of the sea ice meltwater flux in the North Atlantic. On the other hand, in the rapid ramping experiment, we see this interesting transient increase in that meltwater that is associated with this expansion of Arctic sea ice that occurs in that experiment. Now, the blue line here shows one of the two experiments we do to disable this feedback mechanism. So we set the sea ice meltwater flux to a continual pre-industrial climatology seasonal cycle, and I call this MELT-FPI. On the other hand, in orange or red-orange here, we set the sea ice meltwater flux over the North Atlantic to a continual climatology taken from the 2x CO2 climate. In other words, once the sea ice has retreated and there is less meltwater reaching the North Atlantic. And I want to highlight how we interpret these two different experiments. So in the MELT-FPI, in the blue experiment, we've suppressed the meltwater feedback because the meltwater is not allowed to respond to the AMOC changes, but we've also suppressed meltwater as a forcing under CO2. On the other hand, in the orange here, we have suppressed the sea ice feedback, again, by setting the meltwater to a prescribed seasonal cycle, but we're allowing the forcing mechanism of sea ice meltwater, in other words, the reduction of sea ice meltwater that's associated with a 2x CO2 climate. So now we want to understand how the elimination of sea ice as a feedback and as a forcing can impact the AMOC's response to CO2 change. So here I'm showing the AMOC strength now just from those original fully coupled models, again with less AMOC weakening happening when we change CO2 more gradually versus more rapidly. And now I'm showing the AMOC strength in the MELTF-2X scenario. So these imposed warmer climate meltwater, sea ice meltwater conditions. And here in blue, I'm showing the AMOC strength in the MELTF-PI, so the perpetual pre-industrial meltwater conditions. And the first thing we see is that in both of these experiments, so suppressing the sea ice meltwater feedback in two different ways, we've eliminated a lot of the circulation sensitivity to the rate of CO2 change. So we now have relatively similar rates or levels of AMOC decline in these two different experiments. And the other thing I want to highlight is the impact of sea ice meltwater as a forcing, which can be seen as the difference between the blue and the orange lines. And what we see is that when you don't allow the sea ice retreat to have an impact on the meltwater in the North Atlantic, you get a much stronger AMOC weakening seen in blue compared to when you allow the sea ice meltwater to decline consistent with the retreat of sea ice. So this shows that the sea ice meltwater is actually a very strong strengthening or stabilizing forcing on the AMOC, which was something we didn't necessarily expect or know going into it. So now I want to diagnose what's going on with the AMOC weakening, borrowing some concepts from water mass transformation analysis, which is often used in sort of physical oceanography modeling studies. So I'll try to explain this idea. So here we're looking at a schematic of the ocean, and these black lines are indicating isopycnals or contours of constant density. And we can think about a budget of the volume of seawater that exists between two isopycnals, in other words, in a given density class. And the three things that can influence this volume of seawater are mixing of seawater across density classes, a transformation of water across density classes via surface buoyancy fluxes, so the surface buoyancy making the surface water denser or heavier, and then finally overturning or circulation of water out of this domain that we're considering. So there's three different things that can influence the volume of seawater in a density class, and we now rearrange those to think about overturning, which is ultimately what we're interested in with the AMOC, as a function of the surface water mass transformation by buoyancy, the changes in volume of seawater in a density class, and that interior mixing. So for this work, we're just going to focus on the surface water mass component because we know that buoyancy fluxes and their changes are a key driver of AMOC changes in a future climate. And we want to consider this surface water mass transformation associated with the AMOC, which is this deep overturning cell. So we're going to consider the surface buoyancy fluxes only over the densest isopycnals. So what that looks like here is now our surface water mass transformation associated with the AMOC is basically an integral over the areas with the densest surface waters, in other words, the areas of deep convection in the North Atlantic, and it's an integral of the surface buoyancy fluxes over those areas. If all of this was a little bit too much, the main point is that we're going to look at how surface buoyancy drives deep convection in the North Atlantic and how that changes. So here I'm showing the total surface water mass transformation for all 6 experiments. So the upper row is the rapid CO2 ramping, the lower row is the gradual CO2 ramping. And I just want to show the total to show that this does seem to capture some of the AMOC behavior across these experiments with more of a reduction in surface water mass transformation or buoyancy-driven overturning in those experiments that had more AMOC weakening. So this leads us to be confident that we can get some explanatory power by using this method. So now what's cool about this is we can decompose those surface buoyancy fluxes into the components from heat and fresh water. And we see that in the orange and purple lines here, that the heat-driven component of buoyancy-driven overturning is by far dominating the AMOC weakening in all of these experiments. and is explaining the differences in AMOC weakening across the experiments. And this is kind of surprising because we know the only difference in our prescribed setup of these experiments is the amount of sea ice meltwater going into the North Atlantic. So it's surprising that the freshwater term here is playing such a small role. So to understand that further, we're going to decompose this surface water mass transformation in a different way. Now we're decomposing it into those changes in surface buoyancy fluxes, which is what we just looked at the heat and freshwater components of, but then also the change in the area of dense water formation. In other words, the potential expansion or contraction of the deep convection zones over which those surface buoyancy fluxes are allowed to influence the deep overturning. And when we do that, I'm skipping over the equation here, but when we do that, we see in blue that almost all of the weakening of the surface water mass transformation is driven by a contraction of these deep convection zones and a contraction of the area of this dense isopycnal outcropping. In other words, even if your surface buoyancy fluxes didn't change very much, something is happening to contract those areas of isopycnal outcropping, which in turn means that those surface buoyancy fluxes are unable to influence as much area of the ocean. So finally, we want to know what causes the loss of this dense isopycnal outcropping area. And to do that, we can look at the changes in the surface densities. So here I'm showing in the upper row the change in surface density for the MELT-F2X experiment, which had less AMOC weakening. And we see here the black shows the original pre-industrial deep convection zone, and the dashed line shows the later contracted deep convection zone. And we see there's a modest reduction in density that leads to this reduction in the deep convection zone. On the other hand, in the MELT-F-PI experiment, there's no dash line because the deep convection zone actually disappears entirely. And when we break that down into contributions of salinity versus temperature changes to the density, surface density, we can understand why this is happening. So in the upper row, we have pretty equal levels of modest freshening and modest warming of the surface that lead to this modest reduction in density. On the other hand, in the lower row, we have actually a surface cooling, which would lead to denser waters, but that is overcome by a much stronger surface freshening that reduces those ocean densities and contracts the deep convection zones. So in other words, while surface freshening plays little role as a buoyancy forcing, as we saw 2 slides ago, it is able to modulate how much heat loss-driven deep water formation occurs by controlling the area of dense isopycnal outcropping. We can see this also just by looking at the density changes in the entire water column. So here in the...
Just sorry to interrupt you. Would you mind wrapping up?
Yeah, great. I'll skip this one slide and I'll go to my conclusions. The rate of CO2, a few things I want to take away. The general concept is that the rate of CO2 increase is itself a key driver of the global climate. The AMOC weakens more under these rapid CO2 increases due to this positive feedback I've identified between the AMOC and Arctic sea ice. This can be explained by a slowdown of the sea ice freshwater conveyor belt, which by itself is actually a compensating forcing on the AMOC that strengthens the AMOC. And then finally, this freshwater weakens the AMOC not by reducing buoyancy forcing directly, but by suppressing ocean cooling to the atmosphere. So with that, I will leave a few questions up for us to maybe think about discussion. In particular, I want to think about how to jump from these conclusions that I've found in a coarse resolution climate model with a lot of limitations to trying to understand how some of these mechanisms operate in the Earth's climate. And I'll stop there.
Very nice. Thank you very much, Camille. Very interesting work. And again, a lot of information to process for us all. All right, let's open the floor for questions and further discussion. So Jia has their hand up.
I'd like to know, are there any relationship with between the North Atlantic multi-decade oscillation and AMOC? If we know their relationship, and then we may be able to do some projection because you have a time series for 3,000 years. And AMO has a time series, have a cycle about 70 years. So I don't know, you wish to, well, we like to know the relationship.
Yeah, I don't know much about this myself. I know people have looked into multi-decadal oscillations in the AMOC strength being coupled to multi-decadal oscillations, the AMO. And I guess, are you suggesting maybe that could help us disentangle how much of the AMOC weakening signal that we're seeing now is forced versus unforced?
Mm-hmm. Yeah.
Yeah, I think that's a nice direction.
Great. Wade, you had your hand up.
Yeah, very nice talk, Camille. And so my question is that I'm just wondering if the sea ice you modulate on the North Atlantic region, how about the Central Arctic? If we have the CO2 warming and the Central Arctic sea ice can also respond or possibly melt. And then the water, fresh water, due to ice, will be transported through horizontal advection to the deepwater formation region. That can also be part of the CS influence of it, I guess.
Yeah, I'm very familiar with your paper on this, actually.
Thank you very much.
Yeah, so I mean, that process could be happening in my experiments because we're not overriding anything related to the horizontal advection of meltwater that melted in the Arctic and then as liquid came to the North Atlantic. I think what's interesting is even if that process is going on in the background, we see that just by overriding the North Atlantic meltwater, we get this really big difference in the AMOC. So in some ways, I've isolated just this regional impact or the impact of this regional forcing, but there could be interesting things going on in the background with horizontal advection as well.
I see. Great. Thank you very much.
Thanks, Freshwater.
Thanks, Wilbur. Hi, Camille. Really nice talk. Can you go back to the slide that you were on just before you had to wrap up the talk?
Yes, the entire water column slide.
No, the one before that, the one with the area.
Yeah.
Contours on. Yeah. So I'm kind of curious. So when you looked at the PI minus the scenario, you saw this reduced outcropping of the isopycnals, right, area. You don't see anything on the Labrador Sea? I was kind of curious to see there's nothing on that side popping up.
Yeah, one thing that's important to note is where the deep convection zones actually occur in this model and its resolution. So in this model configuration, in the mean state, there's not a lot of deep convection in the Labrador Sea to begin with. So this configuration is kind of missing that deep convection zone. It does a pretty good job of capturing the convection here and then in the Nordic seas, but that one is missing. So that was actually not really included even in the, you don't see it in the pre-industrial.
I see. Okay. Thanks.
Yep.
Yeah, I was just interested in that.
Totally. Thanks.
Mike.
So one question is, could you just give a sense of how the magnitude of Arctic ice, this water export, it compares to the potential melting of meltwater off of Greenland that people are talking about? I mean, which of the effects is likely to be sort of larger? And then just sort of a second thing, I thought also that brine formation from sea ice also contributed to AMOC by putting at least a lot of deep water into the Arctic. Is that still going on, or is that part of the reason in the terms of how much ice formation that is affecting AMOC?
Yeah. So to answer your first question, I've actually I should have done it before this, but I've wanted to for a long time, just convert some of these meltwater rates into units of Sverdrup just to compare them to the types of hosing experiments people do to represent the potential ice sheet runoff. I haven't done that calculation. I suspect the quantity of the meltwater from sea ice is quite a bit less than what we would expect from Greenland ice sheet melting. But I think the key here is where that fresh water ends up and whether it actually approaches the deep convection zones. And there's been a lot of work on sort of if you do hosing in different areas of the North Atlantic versus if you actually run a model with a coupled ice sheet that actually represents the runoff from Greenland. And there's an interesting paper that shows that when you actually include a coupled ice sheet, that runoff doesn't end up reaching the deep convection zones in the model they used. So I can't answer the question in terms of magnitude, but I just want to kind of divert to the point that location and the propagation of those anomalies might be more important than magnitude. For your second question, so there is, the brine rejection is going to be happening a lot more in the deep Arctic, where that thermodynamic production of ice occurs. And so I guess it depends on whether that brine reduction, just like the meltwater that Wei asked about, whether that can actually reach the deep convection zones and contribute to the deep water formation. And so I'm not doing anything in my experiments to override that process. And so I would expect that to operate kind of similarly in my experiments. And it might be contributing to AMOC decline, but wouldn't be contributing a lot to the difference in AMOC decline in my different experimental setups.
Thank you.
And Hailong, you still had a question for Yushi that wasn't answered. And do you want to ask it and discuss this?
Yeah.
Yeah, sure. Ichi, have you read the question?
Yeah, I'm just looking at it.
Okay.
Okay, so yeah, that's actually a good question because I understand that the cloud effect could be model dependent, but in this study that we only check the cloud friction model, and we indeed see the increase and the decrease low-level cloud friction to have the impact on the shore wave cloud feedback. Yeah, so we didn't look any further deeper on the clouds, more specific cloud impact here.
Yeah, in your feedback analysis, the net feedback, cloud shore wave feedback looks like small, but was like average among the whole Arctic. There's some regions that are really positive and some other regions are negative, corresponding very clearly to the prescribed AMOC or freshwater or temperature change. Yeah, I was looking at the panel edge, looking at the,
Yeah, so in the North Atlantic warming hole region, I think you are pointing to this area here, right?
Yeah.
There's a stronger cooling through the shore wave cloud effect. And this shows the difference between the free and the fixed AMOCs. So with the weakened AMOC, that the last northward heat transport in this region will cause a stronger cooling in this region, stronger surface temperature cooling in this region. So I think that's stronger. Yeah, that there's a stronger cooling in this region. So let me think. Cooling in this region. And then it will induce a larger surface heat fluxes or the turbulent fluxes in that region. So that possibly will lead to an increase in the low-level cloud friction in those regions and has enhanced the shore wave cloud feedback in that region.
Yeah, the change in the direction makes sense, but I was just curious why the cloud response is so strong in this model. Maybe that's something other models can have a look and compare to this response for any following up work. Right?
Yeah, thank you for several suggestions.
Yeah, thank you.
All right, thank you all. I don't see any more hands up, and we're getting to the top of the hour, so maybe we should conclude the session here. And thank Camille and Yushi for their very insightful presentations, and for everybody else for attending and for the productive discussion. I'll hand it over to Tony, see if she has any additional announcements to make.
Yeah, thank you, Yuchi and Camille. Thank you, Wilbert. Thank you all for being here. I know folks have to hop off, so I did just put a link in the chat, just a plug. We've got a modelers meeting next Wednesday on the 18th on U.S. efforts in high latitude tipping points research. So I put the link to that event in the chat. We would love to see you there. Stay tuned for more from physical oceanography and the systems teams. But if you've got any topics or presenter ideas, anything you'd like to see one of these three groups discuss, there is a feedback form that I'll also post in the chat. We'd love to hear from the community on what you would want to learn more about or discuss. So if you ever get a moment or have a stroke of inspiration, save that form and you can send us your thoughts. But thank you all again for being here today.
Very nice. All right. Thank you.